Welcome to Lunch and Learn at the Castle Museum. I'm Jennifer Vannette. I'm your outreach coordinator. And today I get to welcome my husband to do a lunch and learn. He is a physicist, a physics professor at SVSU. He earned his PhD from Iowa State. And he actually specializes in condensed matter physics, not astronomy. But he has all these really cool stories that he's always sharing about this. So I think it's going to be very fun. And I'm going to turn it over to you now.
Thank you, Jen. So my name is Matthew Vannette, and Jen already let you know the one thing that I was going to warn you about. I am a physicist, but my background is in condensed matter physics. So this is stuff you can hold in your hand, right? Astronomy is very different from condensed matter physics. So what I'm talking about here is stuff that I have sort of picked up as a maybe well-educated layman, if you will. So keep that in mind as we go along here. And my goal here is to try to give us a sense of where we are in the universe and what that means for us as people. So today, if you go out most places and you look at the night sky, you see something like this picture on the left because we have a lot of light pollution. But if you manage to get a place where you have something that is dark sky, you get this picture on the right. This comes from the 2003 Northeast blackout. A man by the name of Todd Carlson took this in Ontario. What it demonstrates is the difference between what we see and what people used to see. On a dark night, you can typically see about 2,000 unique objects in the sky. These are stars, nebula, galaxies, and 5 at most planets. Okay. The ancients knew about these 5 planets out of the 2,000 they would see on one night. The thing about this is, as you go through the year, the stars we see in the sky are different. So over the course of a single year, you see about 4,500 unique objects. And they keep track of 5 of these things that move around, all right, without photographs. This was important. Understanding what is going on in the sky was really important for how society functioned. So coming up with a model that helps explain what we observe is significant. So what is observed? Well, first of all, we see that the vast majority of objects stay in the same place relative to one another. And when I say the same place, I'm talking about the angular separation between them. Because that's all we can do, is we can look up and we can say that one is there, and that one is there, and there's an angle between them. We have a very handy mechanism for estimating angles. And it scales with your body, so almost everybody can do it. If you make a fist and you hold it out at arm's length, from edge to edge, that's about 10 degrees. If you stick your pinky finger up, that's about 1 degree. Right? If you happen to have a regular pencil and you hold it up, that's about ½ a degree. So we've got senses of what's going on. ½ a degree, the other measure we call that is 30 minutes. Okay? The moon and the sun in the sky, how big would you think that is? Just a guess. How many degrees? As big as your fist?
10 degrees, less than 10 degrees. Oh yeah, 5 to 6.
Right. It's half the size of your pinky. The moon is only 30 minutes of arc. It's ½ a degree in the sky. And when I first read that, I thought, that's a lie. And then I went out, because it was day, I went out and I did this, looking down, and I moved my finger over the sun, and I looked up, and sure enough, that will cover the entire sun. Right? Small things here is what we've got. So the vast majority of things stay in the same relative location, but from one night to the next, they drift. So overnight, we'll see things move from east to west across the sky. But then if we look at the same time the next night, what we see is what was here is now here, and then it comes across. And the next night, it's here, and it comes across. Over time, things drift one direction one night they go all the way across. We wanted to explain this general eastward drift. The planets, however, don't just drift east. Sometimes they go backwards and drift west, and then they return and drift east again. This retrograde motion made them easy to spot, right? So we got to explain this if we want to know what's going on. And the question is how? How do we explain what we observe? Because that's what we're trying to do with our science. And the first way we could think about doing this is what we call a geocentric model. The Earth sits in the middle because we don't feel like we're moving anywhere. And when we look out, everything is surrounding us. Clearly, we are the center of the universe, right? And that's an important and privileged place to be. The problem with it is you run into issues with the way the planets could move and how they can line up and how they will go with the different stars in the background. The geocentric model is problematic. Several people through history recommended that maybe the sun was at the center of the universe in a heliocentric model. And Nicholas Copernicus, a Polish-born, well, in Krakow, it wasn't Poland at the time, mathematician and philosopher and scientist, advocated for a heliocentric system. The issue was, he said, all of the planets will move in perfect circles around the sun, and they will always move at constant speed. And the reason for this was circles are perfect in this idea. And the universe created by God is going to be perfect. And what's more perfect motion than uniform motion, constant motion? The issue with this is his heliocentric model then does really poorly in predicting things. All right? So it's maybe not the right way to go. So we get to the guy I want to really start with, and this is Tycho Brahe. Brahe is an interesting fellow. He was born kind of wealthy into some money. At about, it was 20 years old, he got in an argument with his third cousin, and they decided to have a duel to settle it in the middle of the night. And in this sword duel, Tycho loses his nose, and he gets a scar cut across his forehead. So in order to handle this nose, he gets a prosthetic nose, and he has a brass nose for everyday wear. But then he has a gold and a silver nose that he would get out and stick on his face for parties and important events, right? Tycho claimed, though, that the Earth cannot move. And the reason the Earth cannot move is when we look out at the very far stars, the fixed stars, we do not see what is called parallax. And a way to demonstrate parallax here, and I'm already way behind time because that's what physics professors do, is hold one thumb up and then your other thumb up, one far away and one near. Now close one eye and move your head until this thumb blocks that one. Then switch eyes. And what you see is that the thumbs move with respect to one another. You didn't shift them at all. But because your perspective shifts, the relative location shift, the angular separation changes. Tycho said, well, because we don't see that with the stars, the Earth can't be moving unless the stars are like absurdly far away, right? Like maybe 20 times further away than the planet Saturn is, okay? That was where he said, we got to draw this edge. Tycho coined this term nova, and in 1572, there was an observed new star. And this is what Tycho called it, a stella nova, a new star. And this observation is what prompted him to get into astronomy. He came up with what's called a tychonic system. We'll get to that. It's sort of a hybrid geocentric, heliocentric type mix. He was a master of naked eye astronomy, and he was the last astronomer to really do good naked eye observations, finding the positions of things to within 2 to 3 minutes of arc. So cut this up, divide it into 60 pieces, and he could find it to within 2 to 3 of those 60 pieces. Really, really precise. And he collected his data over about 30 years, so he did a lot of work to try to get this. His model is based on this notion that the Earth is the center of the universe, the moon orbits the Earth, and the sun orbits the Earth. But then Mercury, Venus, Mars, Jupiter, and Saturn orbit the sun. So we've got one wheel where the sun goes around, and we've got all of these other wheels running around the sun, right? It's very much a wheels within wheels view of the world. And he was convinced the key to demonstrating that he's correct is to get very high quality, accurate measurements. So he convinces the King of Denmark to build him an observatory on an island between Sweden and Denmark. He named it Uraniborg, the castle of Urania, who was the muse of astronomy for the Greeks. So an appropriate name there. What's interesting about this is one of the first observatories that was built entirely by government funds, only to do research, right? So he starts this notion of, if we want to do work, we ask the government for money to help us out. There we go. The other thing he did, though, was he said, if I'm going to figure this out, I need to have well-organized and easily searchable data. So Tycho basically invented the concept of a laboratory notebook, of this is how I keep track of my data. Right? This is a clever individual that he's working with. He put on his castle grounds an instrument shop, because if we're going to do work, we have to build high-quality instruments. He was able to get his precision by using screws to adjust the positions of things. So he would set up his instrument where he's going to sight on a pivot, and then down here he would have a screw that he could turn. So it would push it very, very small amounts. And that would allow him to make very precise measurements, his 2 to 3 minutes of arc. He also made his instruments very large, because if I'm measuring degrees, the angle between the stick and my hand stays the same all the way out. But the arc it swings is very small at my fingertips, but it's huge at the far end. Does that make sense? So if I can, instead of measuring how far this is rotated at my hand, if I measure it out at that end, I can get a lot more precision. Right? This quadrant used to measure angular positions was about 2 stories tall. Okay? So huge instruments here. His precision was so great that towers where people normally built their observatories, he could recognize when the wind blew. Or he could recognize if it got hotter or colder, his instruments would shift. So he said, we have to build my observatory underground. Right? This is the drive that happens when you say, I want to know. Recognize our problems, and then we work to fix it. The thing about Brahe is he wasn't very good at math. Right? He could make observations like nobody's business, but he wasn't very good at math. So in 1600, Johannes Kepler starts as one of Brahe's assistants. Brahe had about 100 people working under him on different projects. Kepler was a hardcore heliocentric. Like Copernicus is right. But he would lie about that when it was convenient or when it was helpful. Right? So to get his job with Tycho, he told him, no, I like your system, it works well. Right? Because Kepler believed that if he could get access to Brahe's data and work with it for just 2 years, he could prove the heliocentric system was correct. Okay? Now, Brahe guarded this data very carefully. He did not want people to just make copies of it and take it out, because this was his life's work. He allowed Kepler to look at it and do calculations with it, but he couldn't take the data with him. Okay? If you come back, I didn't put it up on that one. Brahe dies in 1601. Kepler starts working for him in 1600. And historically, this is raised eyebrows because of motivations. After Brahe dies, Kepler does something that is of questionable morality. He steals the data in the middle of the night. He basically goes into the observatory, grabs all of Brahe's notebooks, and then leaves before Brahe's family can get in there and go through his effects and find anything, right? He did this because he knew the family would not give him the data because Brahe didn't want him to have the data. Now, Kepler claims that on his deathbed, Brahe said, "Publish my data," right? Which is real convenient when that's what I want to do, and the guy can't come here to tell me about that, right? But it didn't take 2 years for Kepler to work through things. Even though he had the data himself, it took him 8 years to work out how the system would function in a heliocentric system. So he vastly underestimated the difficulty of the problem, which is fine. But he gets this, right? And he comes through and he says, 1609, there are 2 rules for how the planets orbit the sun. 1, on ellipses, not perfect circles. 2, they move at different speeds as they go around the ellipse in what's called this equal areas law. And I'll show you that in a moment. Took him another 10 years to work out what's called Kepler's third law, and we'll talk about that one as well, the cube squared law. So, right, determining actually how to fit the data to the heliocentric model only took Kepler 10 times as much as what he estimated. And any researcher will tell you that is the most difficult thing to do. How long is it going to take you to do this project? How long are you going to give me? Right, that's the best answer. The big thing that Kepler does is he abandons the perfect circle and he makes an ellipse. Put the sun at one focus, and at the other focus it's just empty. So now if I put 2 pins here and I make a loop of string, I can put a pencil and stretch the string out, and that will draw an ellipse. He gets rid of the notion of uniform speed and this equal area business. Basically, he says, I draw a line from the planet to the sun, and then that line is going to define an area or sweep an area as the planet moves. And let's say the planet starts here and it moves here and it takes 3 weeks. I get this shaded area. At some other point in the orbit, the planet starts and it moves and it takes 3 weeks. I get this area. Those 2 areas are equal. That's the way it ends up. Okay? Kepler's data tells him this has to be it. All right? And how is that possible? And he didn't know. He had no reason for it. He just said it is. Why do they move on ellipses? I don't know, but they do. Right? It's a big thing that Kepler did. We call this phenomenology now. He looked at the phenomenon and he said, this explains the phenomenon. Right? But he didn't have any sort of underlying theory to why it did it this way. He was also able to measure the distances between the sun and the planets compared to the distance between the Earth and the sun. So he had no absolute units. He could just say, if I take the Earth-Sun distance as 1, then Mars is this far away, and Mercury is this far away. Everybody is in somewhere between about 0.6, I think, for Mercury, out to maybe 15 for Saturn. But I don't know exactly what these lengths are. So we've got all this relative size stuff. This was significant because it sets up a very different view. We're not in the center of the universe, and we don't move on perfect circles, and we don't move at constant speeds. The sun is now at the center of the universe. Right? It's still an important place, but we go around the sun. And from a religious perspective, we could justify that by saying, well, right, of course the sun is at the center. It's what gives us our light, right? Just like God. So that makes sense, and everything is okay, and maybe we can sort this out. So contemporarily with Kepler doing his work, we've got Galileo. I think many of you probably know of the name Galileo. considered by many to be the father of modern science. I disagree. He's one of the people who contributed. We have Brahe coming up with, this is how you keep track of data, which is an important part of science. We have Gilbert, who's a British physician, who describes how you do experiments and then lay out description of experiments so that other people can repeat them. He does that before Galileo. But, right, the big thing that Galileo does, we'll see, is he overturns Aristotle in a lot of ways. It's claimed that Galileo is the first person to use a telescope for astronomical observation. He stops this notion of we'll do it all naked eye. That's questionable because if you give a tube to a kid, they look through it, and they'll look at the sky, right? Everybody who gets this tube, the first thing you're going to do is start looking around and what can I see? That's where it is. He gets credit, and that's where credit goes. Like I said, what he did best was overturn this dogmatic adherence to ancient views. One of the important things that we have, Galileo uses his telescope to observe Jupiter. And if you look up at Jupiter at night, you'll see something like that. There'll be other dots, right, other stars around it, but you look up and you say, oh, there's that Jupiter. I can see it right there. Galileo takes his telescope and he aims it at Jupiter. And what he sees is something like this. And to us, we're like, well, that's kind of anticlimactic, right? Except this was the first time, potentially, on Earth, anyone had ever seen it. Jupiter is this dot. I aim my telescope. It is not a dot. It is a disk. And what's more, what happened to my TV? Oh no. What's more, we'll come back when it comes back on. The top one is the power.
Yeah, it's on. I just unplugged it.
He saw these three new dots that weren't there before, right? If I look up at the sky and I see this Jupiter dot, and then I look through my tube and I see, no, it's a disk, and there are three other dots next to it that I can only see with the telescope, the question is, what else am I missing? What else am I not seeing? Because all I can see is my naked eye stuff, right? These three dots that Galileo sees and records change the scope of the universe in ways that I cannot understand, right? It's hard for me to fathom. Because no one had ever seen them. And has anybody ever looked at Jupiter through a telescope? Okay, so I am going to set up observing nights. I got to do this because if you all haven't, it's got to happen. No matter what age you are, it is life-changing. Okay? Because you see things, you see these three dots. This changes everything, right? A revolution begins with it. Now Kepler, he takes Galileo's telescope and he makes a tweak to it so that he can get clearer images that are easier to work with, right? Now these images are not perfect, though. There's this thing called chromatic aberration. If I want to look at the blue images in focus, then the red parts are blurry. And if I want to look at the red parts in focus, then the blue parts are blurry. How do I fix this? This is an issue. One way to fix it is the length. Instead of making the telescope this long, I'll make the telescope this long. Because then I can use a thinner lens, a weaker lens. And that fixes the chromatic aberration a little bit. If I want to see things that are bright, I want to use a large diameter lens, right? My eye can only bring in light that hits an area right about the size of, what, maybe the end of a push pin, if my pupil gets fully dilated. Galileo's telescope had an aperture of about this big. If I can make an aperture this big, I get more light. If I go this big, I get more light, right? So I want to make these things bigger and bigger so I can get more and more light, longer and longer, so that I can fix the chromatic aberration. So by the time Kepler works out his third law, it's the square of a planet's orbital period divided by the cube of its distance from the sun. It's common to all planets. Okay, it's just a calculation that he can do. He doesn't know why it's this way, but again, it is. Kepler looks at Galileo's moons, keeps track of where they are going back and forth around around Jupiter rather. And he says, the three laws that govern orbiting planets around the sun also tell me how to predict where these moons are going to be around Jupiter. So these things are orbiting around Jupiter according to the same rules that we go around the sun. This is significant again, right? Because a rule we came up with for one situation applies to a completely different situation that we didn't even know existed. That's science right there. That's what we do with our science. Now I want to bring in two of these astronomers because now this revolution has begun. We're going to start accelerating what we can discover. Johannes Hevelius, he took this notion of, if I want to fix chromatic aberration, make a long telescope, to an extreme. He was independently wealthy, had a very patient wife. He had an observatory that he built over 3 houses, and his telescope was 150 feet long, right? So that he could get rid of this chromatic aberration. That's the big thing he contributed. Cassini did something that was really, really important. Kepler could give us the relative distances between everything. Cassini, when he was the director of the observatory in Paris, sent a colleague to Cayenne in French Guiana off of the South American coast. And on the same day, they made a measure of the position of Mars that they could see when it was in opposition to the sun. So it was the sun, Earth, Mars in a straight line. And he said, the angle that I measure and the angle that my partner measures are different because of parallax. He used that angular difference and the known distance between the 2 points to then say, this is how many miles apart Earth and Mars are right now. And once he got that, he was able to calculate the distances for everything in the solar system. And it turns out the solar system was way bigger than we had imagined, right? This happened in 1672. So for like 350 years, we've known the solar system is really big. Now comes along Newton. The big thing that Newton does is he gives us an underlying theory for why all of this happens. In this Principia, what it's called that, in 1687, he invents calculus. I put that in quotes because calculus had been around for a couple thousand years in one form or another. But he lays out these laws of motion and gravitation. And he delayed publishing this, in part because he was trying to predict what the moon was going to do. And he had bad data. He was looking at tide timetables that were wrong. And he had a sailor friend who looked at his timetables and said, why are you using those? Those are wrong. Gave him the right ones, so he was able to calculate again, and he said, my model works when I have the right data. That gave him the way to demonstrate that he knows what he's talking about. What he's less known for is his work in optics, which he did first. The big thing for this is the dimming due to distance. As you move away from a light, it gets dimmer and dimmer. And Newton gave us how dim does it get as I move away. That relationship, distance to dimming. That's important because it'll let us say, when we look at the star, it's this bright. If I know how far away it is, I know how bright it is at its source. He worked to correct chromatic aberration, but he said, I can't do it. It's impossible. No one can do it. A story about this is someone figures out later on. I forget the name of this person. And what he does is, he says, what I have to do is I have to make a lens that's shaped like this and a mating lens that's shaped like this that I bring together. They got to be of different materials. To test this, he needs to have these lenses made. So he goes to one lens maker and says, make me this, please. And he goes to another lens maker and says, make me this, please. And these two lens makers subcontract to the same guy. And this guy is making these lenses, and he recognized they're going here, but ultimately they're going to the same person at the end. Why would someone go through all this trouble to hide the fact that they're making this and this when they mate exactly? So the subcontractor puts the lenses together because that's what they're going to do, shows that chromatic aberration is fixed, and he gets the credit. Brahe was onto something. Have your own instrument shop. But because Newton said, I can't get rid of chromatic aberration, I'm going to make a mirror telescope, and he builds a reflecting telescope. And that's a huge, huge innovation because it allows us to make telescopes that are large and not heavy. Glass is very, very heavy. But if I can have a thin sheet of metal, it's not nearly as heavy. All right. Now, I'm going to run over time, so I'm going to have to move quickly through here. I'll let you know, Herschel is the guy who discovered the planet Uranus. In 1781, he did it by accident. He was looking at the sky, looking at the sky, looking at the sky, looking at the sky, and he recognizes this. Yes, it was a complete accident that he found this. And he said, what am I going to name this? Should I name it after King George? People on the European continent didn't like that. They were calling it Herschel. At the end of the day, we settled on Uranus because that is the father of the sky within the Greek system, right? Running this way. So, right, 1781, we add another planet to our system. Neptune is not visible at all to the naked eye. Galileo noted that there was this blue star near Jupiter, which, according to everything, would have been Neptune, based on where it sits. There was another scientist in 1795, Lalande was his name, whose staff made a couple of observations of this blue star, but they thought it was a mistake because it moved, right? So they said, something's not right here, we're not measuring this correctly, and they moved on from it. John Herschel, William Herschel's son, accidentally sees Neptune in his telescope, but doesn't recognize it as a planet. Instead, this astrophysicist, Leverrier, he predicts the existence of Neptune because he's watching where the planet Uranus is moving, and he says it's not moving the way it should according to the laws that Newton gave us. So in August of 1846, he says there should be another planet, and it should be at this position in the sky, it should be this far away, and it should be this big. By the end of September, this planet is observed. Okay. Now, the orbit of Uranus is about 87 years. And it was only 65 years from the time it was observed to the detection of Neptune. It took less than one time around for us to use Newton's laws to say Neptune exists, right? This is incredible because we're making the universe bigger and bigger and bigger as we go, but how big is it? We want to know, how do we measure this position? How do we keep track of time? If we can do this, if we can measure the angular positions in the sky, if we can keep track of time very carefully, then we can start to figure out where things are. And as we improved, parallax becomes a very reliable method for measuring distances to things that are kind of near. And what we started to discover there was Tycho's 17 to 20 times the distance of Saturn's orbit is absurdly small, right? That's a tiny, tiny universe. It's way, way bigger than this. So this is a photographic plate of the Andromeda Galaxy, but we didn't know it was a galaxy when this plate was made. It was a spiral nebula, and they thought it was stars that were forming. Within this nebula, over time, people observed lots of novas, bright stars, appearing and then disappearing, appear and then disappear. These nova are really dim compared to other ones that we see. They're far away. One speculation was this is an entirely different universe. We're in our universe, and this is a completely different universe from us. It would very much help us to know how far away this thing is and what is it doing. Enter Henrietta Leavitt. Leavitt worked as a computer at Harvard, the Harvard College Observatory, under Charles Pickering. This was at a time when women were not allowed to use the telescopes. They couldn't look at the telescopes, operate them, or anything like that. But they could look at the photographic plates. So Pickering gives Leavitt the task of analyzing the behavior of this certain type of stars, which are called Cepheids variables. These are stars that get brighter and dimmer over a fixed period. Different stars have different periods, and they get to different brightnesses and different dimness. So Henrietta, working with film plates, is looking at these stars get brighter and dimmer over time, and she's analyzing several hundred of these. She works out that there's a relationship between how bright they are and the period that they vary their brightness, right? A plate something like this, where this is the negative, as that gets darker, that's indicating a brighter star. So she's looking at how big is the dot, and then saying this is how bright or dim it gets. And this is the one plot that I really show. And as a physicist, it's hard to give a talk without showing plots. This is a star at its dimmest, and this is the same star at its brightest. And we go up and down this way. And you've got these two slopes. Along here measures the period. It's really the logarithm of the period for how it gets brighter and dimmer. And along here is what we call the intensity, or the brightness, the magnitude. As things get brighter, their periods get longer. And it's this nice relationship. She's able to now use this to measure the distances to things. Turns out to be up to about 20 million light years away. This is accurate. Okay? Now we need to know how fast things are moving. We can look at stuff. Get something glow really hot, it'll give off a continuous spectrum, a rainbow like this. The sun gives us a rainbow because it's very, very hot. It's called black body radiation. And as the temperature goes up, you get some shift like this, and we can see what goes on with this. I lied, there are two plots. Atoms don't emit continuous spectra. Atoms emit lines. And these fingerprints are unique to each atom and molecule. If you look at gas that's giving off light through atomic emission, you can tell what the gas is made of by looking at these lines and measuring them. Now, if I take this spectrum and shine it through gas, I will get this spectrum. The colors the gas emits disappear. They get absorbed. This is how we can say Jupiter had this composition before we sent any probes to it. This is how we can say the sun has this composition in its atmosphere. This is the solar spectrum with all of the absorption lines. Each of those lines corresponds to a particular element that's in the sun. We were able to account for all of these lines using every element on Earth except for one small set. This one small set then belongs to an element that exists in the sun. We have a heliocentric, helios. That element must be helium. That was how helium was discovered, was that it exists on the sun by looking at these lines. Now the thing is, if something is moving toward us, all of these lines shift toward blue. And if something's moving away, they're going to shift towards red. But they get squished if they go blue, and they stretch out as they go to red. It's not uniform, so it's kind of a mess to work this out. But based on how fast it's moving toward or away, we get different blue shifts and red shifts. This becomes our speed measuring device. Hubble, this is the man that we know from his telescope that we get now. He uses Leavitt's law, and he determines the distance to Andromeda is about 2.5 million light years. That's very, very far. The size, he measured the size of the Milky Way galaxy. It's about 87,000 light years. Right, so this thing is way far away. He also used these Doppler shifts to measure how fast things are moving relative to us and what direction. In our neighborhood, that is, in the nearest, say, 15 million light years around us, things are kind of moving all around. Nothing farther away, faster away, or closer, or anything like that. But as things get further and further away, everything starts to move away from us. And what's more, the further away it is, the faster it's moving away from us. This is Hubble's law, and this is the notion of an expanding galaxy. If everything was expanding, at some point it had to be close. That's our thought. We're on it backwards, right? We call that the Big Bang. So, brief history lesson here. About 13 billion years ago, 13.8 billion years ago, the universe came to be. And what I mean is the laws of physics that we understand started to be applied. At this Big Bang, okay? Within about 1 nanosecond, so 1/1000th of a second, electrons form. We got to wait an entire microsecond, 1/1,000,000th of a second, protons form. And now we've got to wait all the way to 3 minutes, and then hydrogen forms. And now stuff just kind of evolves for the next 13 billion years, right? Most of the fun stuff in terms of formation happens very early. Am I doing something wrong? This, and I'm out of time anyway, aren't I? I've gone way over. So about 13.8 billion years after hydrogen forms, Penzias and Wilson are using a radio telescope to examine what's going on, and they can't get rid of this hiss that's in their telescope. They do everything they can think of. They clean up their electronics, they clean all the dust out of it, they stop pigeons from pooping in it to get rid of this, and they can't. It turns out what they're seeing is the time when hydrogen formed. They have this echo of when hydrogen formed everywhere in the universe. And we can now make a map of that. We call it the cosmic microwave background. And this is showing Earth is in the center, and it's the edge of the observable universe. Now, red areas are where it's just a little bit hotter, and blue areas are just a little bit colder. And trying to figure out why these hot and cold areas exist is really important for us figuring out where we are. So light takes time to reach us. We want to look for old galaxies, so they're going to be far away. We need a big telescope with very little interference, so we want a big mirror or a lens, and we want it way high up. Want it in space, glass is heavy, so we're going to make reflecting telescopes. Far away means moving fast, redshift. So our famous telescope is Hubble. And the reason I'm holding this is because this is how big Hubble's mirror is. So Hubble's primary mirror is about 2.5 meters in diameter, collecting light. Your eye, Galileo, Hubble. A lot more light comes in here. And we use Hubble to take pictures of Jupiter, what Galileo saw. This is the Crab Nebula. It's about 6.5 thousand light years away. That's from a supernova at about 1050 is when the supernova. Down here, there's another big galaxy pulling the stars toward it. That one's about 120 million light years away. Right? This is the first 1,000. Those we know are stars that we didn't know existed. But Hubble is optical. The James Webb Space Telescope is a marvel of engineering. Red shifted light. We want to see the infrared. 6.5. This is 6 meters. That's Webb's telescope. All right, the primary mirror. Rotated around. Okay, this is not a small thing that we sent up. Shield, this part right here, it's the size of a tennis court, and it's designed to. When we set it up, it had to be folded because you can't have a tennis court on the end of a rocket. Right? So they got it up and they had to get everything fixed. It's a bunch of hexagonal mirrors. This was the first image they could get from the mirrors. So then what they do is they say we're going to line everything up onto a grid and we'll identify each of them. Now, we've got all this distortion. What we've got to do is take each of our mirrors and make them smooth again by putting little tiny pressures, moving them by micrometers. Start with them blurry. As we move them, we bring every individual dot into focus. I've got them focused now. I want to take all these dots and bring them onto one spot. They did this. Now we've got to make each of the individual mirrors line up with all of its partners. Okay? One of those segments, imagine it's the size of Texas. The whole mirror is the size of the continental United States. Each section is flat to within a millimeter. And the whole surface is the same to within about 5 millimeters. All the way across the United States. That's the scale we're looking at here. Once they got that final alignment set up, we get what I consider to be the most amazing image ever. This was the test image, aimed at a boring old star in our galaxy. You can't see this star at all. Most people with telescopes can't see this star. It's so bright, it's washing everything out. But as a test image, Webb sees all of these galaxies, which we had no idea existed. Some of these galaxies, they've been aged, they figured out the age, are on the order of 13.6 billion years old. In the first 200,000 years of the universe, they formed. They're all the way out there. And this was just in one generic direction. What if I went this way? Right? There is so much stuff. And we started with this idea that we are the center of the universe. We are the most important thing that exists. And we shift ourselves off a little bit. No, the sun is the most important thing in the universe, but we matter a lot because there isn't a whole lot else. But this test image shows there's so much stuff. There's no way we are important to the universe. We do not matter to the universe. This image tells me you have to matter to me. Because in this image, I'm told none of us matter outside of it. This is the image that tells me humanity has to care about humanity. So where are we? We're on a tiny planet next to a boring star in an average galaxy that is one of hundreds and hundreds of trillions. We're not special. Not to the universe, so we should treat each other as if we're special. And if we are unique, if we are the only life, then that's even more important for us to take care of each other. Because if we're it, right? This is why I do science. I'll end now, and I'm over time, and I apologize.
You're fine. There are a few minutes for questions if anyone had a question.
What is the degree of arc that we're looking at in that photo?
So this particular image, I don't remember exactly how large it is. I can show you, I had other slides on here, but I wanted to give my little bit. This is Webb's first real deep field image, scientific one. This one is a grain of sand held at arm's length. Okay? Well, no, this one is smaller. Yeah, this guy is going to be larger than that. It might be on the order of a pinhead. Right? And it's an accident, right? Those are artifacts.
I hope I understood what you were saying well enough to ask. So, when you were talking about the atomic light spectrum, so if there are elements that are not present on Earth, would we be able to recognize them using that technique?
Yes.
Okay.
Right, because what we would do is we would say, we can't account for those lines.
Okay.
And if I can't account for those lines, then I would say there must be something else.
Okay.
Right? And from those lines, astronomers would be able to tell you these are the chemical properties of this element.
Okay.
Right?
Is there any chance that there's something that we wouldn't even be able to recognize because we don't know how?
It's really unlikely.
Okay.
Because the periodic table is full.
Okay.
Right? We step through with the periodic table, number of protons increasing, and we fill all the way up. Right? There aren't any gaps for us.
Okay.
So it's unlikely that we would see something in the middle of everything, maybe at the very, very high, heavy ends, but even there it's not likely.
Thank you.
So, right, the sun has been around for about 4.5 billion years. Okay. We are probably a third generation star. Meaning that in our neighborhood, some star formed, it went through its life cycle and died. And then another star formed from what was left there, went through its life cycle and died, and then we formed. And the reason we know we're not first generation is elements heavier than iron exist on Earth. And the only way we can get those elements is through very, very explosive and energetic processes, stars exploding. Well, if a star explodes, it has to form first, right? So our sun at 4.5 billion years old is middle-aged now. Does that answer your question? Oh, those other galaxies, they're 13 billion years old, right? They've, maybe? Right, our galaxy. Right, well, I don't know. If I look at my clock, say it is October 11th, 2022 at 1 o'clock in the afternoon in Saginaw, Michigan. I do not know if that galaxy exists now in its space, right? I don't. What I do know is the light I'm getting from it tells me it existed at this time, right? And because it was existing 13 billion years ago, I'm able to look at it as it was 13 billion years ago. Right? So could these galaxies have completely disappeared? Yes. There's a distinct possibility that they have. But there's likely other galaxies that would have formed because we're here, right? Our galaxy is here, so we would expect our galaxy to be generic. Does that make sense? Merged, collided, all sorts of stuff. Yeah, as we call, yeah.
Has this Webb telescope made any advancement in time travel theories or?
No, right? It's really unlikely that time travel is going to be anything that's possible. Right? The joke we make with our students is when they come in and I didn't get my homework done, right? Well, let me lend you my time machine. It's half finished. It goes forward at one speed, right? You do the rest. The rest is left as an exercise. And it's hard because we don't, how do I want to say this? I think many scientists, myself included, don't have a good handle on time and what it is. Okay? Yeah. I know I get older, but, right, and it's hard. It's an interesting question, though.
Okay, well, I think we definitely all have a
I'm
lot
sorry.
to think about, and I don't think that many of us expected bronze noses and theft and everything else as part of it, so that was really interesting, so thank you very much.
I'm sorry if I went fast.